We're working through the proof that anything provable from the axioms of PA+ has a bounded deduction in Z infinity. We've shown that the first group of axioms is deducible, so the next thing to consider is the second family of axioms, the induction axioms. These have the form not phi of 0, or there's an x so that phi of x and not phi of x plus 1, or for all x phi. Remember, with this notation, phi by itself is the same as phi of x. We'll first show that there's a deduction of the set with the three disjuncts, a deduction of not phi of 0, comma, there's an x phi but not phi of x plus 1, comma, for all x phi. And we'll be able to give an ordinal bound on this deduction. The exact bounds from counting steps are in the notes, but the exact bound isn't so important. What matters is that we can give some bound and that the bound is less than epsilon 0. Working backwards, we're going to want the last rule to be for all introduction. So we need to find, for each n, a deduction of not phi of 0, comma, there's an x phi but not phi of x plus 1, comma, phi of n. Naturally, since this is the induction axiom, we'll find this deduction by induction on n. When n is 0, we have a deduction of not phi of 0, comma, phi of 0. And then we can use weakening to add this extra, there is an x so that phi holds of x, etc. So suppose we have a deduction of not phi of 0 dot 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 phi of n, and what we want to do is get a deduction where we replace that n with n plus 1. Well, we have a deduction of phi of n plus 1, comma, negation of phi of n plus 1. And we want to use and introduction to combine the phi of n from our old deduction with the not phi of n plus 1 here. Before we can use and introduction, we have to get the side formulas to match up. The definition of the and introduction rule requires that there be a single set gamma of the side formulas on both sub-deductions. So we use the weakening rule. This is a common pattern in deduction, using weakening in this way to make the side formulas match up. After we use and introduction, we have not phi 0, comma, there's an x where phi holds of x but not x plus 1, comma, phi holds of n but not n plus 1, comma, phi holds of n plus 1. So we use exists introduction. If phi holds of n but not n plus 1, that is an x, so that phi holds of x but not x plus 1. And then contraction lets us combine these two existential statements because they're two copies of the same sentence. So for each n, we get this deduction of not phi of 0, comma, there's an x so that phi holds of x but not x plus 1, comma, phi holds of n. And then we count the height of this deduction inductively. When we do this counting, what we discover is that the nth deduction has height at most 4n plus 2 rank of phi plus 1. In order to finish this deduction using for all introduction, we need to bound each of these deductions with some ordinal beta n, so that for very large n, tau of beta n is bounded by n. Taking beta n to be rank of phi plus 4n plus 1 is never going to work. Tau of rank of phi plus 4n plus 1 is more than 4 times n, so no matter what tau of alpha is, once n is big enough, tau of rank of phi plus 4n plus 1 will get bigger than n. Instead, we'll take 4 to be the coefficient of omega. There's a general claim about ordinal bounds we need here. If we can deduce gamma with bound rank of phi plus 4n plus 1, we can also deduce gamma with bound omega times 4 plus rank phi of 1, comma, n. To see this, imagine going up from the deduction at the bottom. So the ordinals are counting down. We know that there are, at most, rank of phi plus 4n plus 1 steps, because we know the deduction is bounded by rank of phi plus 4n plus 1. So after going up rank of phi plus 1 times, we must have counted down to omega times 4, and there are 4n steps left in the deduction. Since the numeric bound is n, we're allowed to count down from omega times 4 to omega times 3 plus n. And then we can go up n more steps in the deduction. So we count down the ordinal n more times. We've counted down to 3n steps left, and there are omega times 3 left in our ordinal. Continuing like this, we have exactly enough space to count down all rank of phi plus 4n plus 1 steps before these new ordinal bounds hit 0. Returning to the deduction we're trying to construct, for each n we have a deduction of not phi of 0, comma, phi of n, with bounds omega times 4 plus rank of phi plus 1, comma, n. So now we can use for all introduction, and we get the bound omega times 4 plus rank of phi plus 2, comma, 0. We don't want to deduce these 3 separate clauses, we want to deduce a single disjunction. So we can deduce the thing we actually want from these clauses by using the or introduction rule. So if we apply the or introduction rule to not phi of 0, we get not phi of 0 or there exists an x phi and not phi of x plus 1. And then we can apply the or introduction rule again to exists an x phi and not phi of x plus 1 to get the same clause. And then the contraction rule lets us combine these into a single disjunction. This is another of these common patterns in Z-infinity deductions, that we have 2 clauses with a comma, and we want to combine them into an actual disjunction, and we do this with 2 or introductions and a contraction. Indeed, that's exactly what we have to do a second time, to combine this disjunction with the for all x phi. We apply 2 or introduction rules, and then we contract them. This whole process added 6 steps at the very bottom of our deduction, so we can just add 6 to our ordinal bounds. So in the end, Z-infinity deduces the induction axioms with bounds omega times 4 plus the rank of phi plus 8.